What is abstract algebra? Trying to define what abstract algebra is, or trying to even define what is mathematics, it's something very difficult, and not everyone agrees to one definition. However, here is my definition of abstract algebra, and see what you think about it. So, it took me an embarrassingly long time to realize that abstract, the word abstract in abstract algebra, it's not an adjective, it's a verb. Because abstract algebra is a way of doing math in that we take something algebraic and then we abstract that algebraic object to create other objects that have similar properties so that we can prove theorems about that new class of objects. So in this video, let me show you how to do that, how we do abstract algebra, and do this in particular with the most basic algebraic object, the integers under addition, and then out of that create some new class of objects that is of a lot of interest. This happens all the time in algebra and has been a very profitable way of doing mathematics. And in this way, we've created groups and rings and fields and modules and Galois representations. And all of these objects have found amazing applications within math and outside of math in applications to the real world. So let me show you how to do that, how to abstract algebra. So let's learn how to abstract algebra. Just as a reminder, this is a first course in abstract algebra, and this is the very first video in this playlist of courses on abstract algebra for undergrads or for college students. So how do you abstract algebra? These are the easiest steps. First, we're going to identify an algebraic object of interest, such as the integers. We're going to identify its basic properties and state them as axioms. For example, we know that the integers, the addition is associative or commutative. Those are going to be our axioms. Then we're going to define a class of objects that satisfy those axioms that we've sort of abstracted. And then we're going to prove theorems about those objects in the class X. And then we profit and repeat, and we do it all over again. So let's get started. So here is the integers. So the integers, we will actually come back to this in a later lecture and write down axioms that define the integers themselves. But for now, let's use this sort of caricature of the integers that we're all comfortable with. The integers are the numbers ... -3, -2, -1, 0, 1, 2, 3. And well, the integers have some algebraic structure that comes from the fact that there is an addition. So the integers have an addition operation. The addition operation is what we call a binary operation, which goes from z cross z to z. Or in other words, we say that the integers are closed under addition. And this addition satisfies properties. So what properties does it satisfy? I'm going to start with the fact that the addition is associative. That is a property that we take for granted many times, that it's really important. So what does that mean? It means that a plus b plus c is equal to a plus b plus c for any integers a, b, and c. The addition is also has the following property: there is a zero element. So there is a zero element in Z that is the neutral element with respect to addition. So it's an element such that A plus 0 is 0 plus A is equal to A for any integer A. It also has the following property. It has the property that there are inverses. There are additive inverses. So for every integer, there is some other integer that when we add them up, we get 0. That's sort of a defining property of the integers themselves. So for every integer a, there is another integer which we call minus a, such that when we add them together, we get 0. And we add them in the other way, we also get 0. And then, of course, also we have the property that addition is commutative. And that means that for all a and b integers, we have that a plus b is the same as b plus a. These properties are the very basic properties that I'm going to call G1, G2, G3, and G4. And these basic properties, we're going to see that there are many other objects that satisfy these properties. For example, for example, the rational numbers. The rational numbers, so quotients of integers m and n, such that n is non-zero, the rational numbers they satisfy G1 through G4 because, the addition of the rational numbers is associative. There is an element 0, which is in here. 0 is the fraction 0 over 1, for example, that works as the 0 as the neutral element with respect to addition. We have additive inverses. So the additive inverse of a over b is minus a over b. And we have commutativity. So we have that Q satisfies the same axioms that we've abstracted from the integers. The same way, we have that, for example, the real numbers under addition, or the complex numbers under addition, they also satisfy these properties G1 through G4. And there are other examples. So, for example, if you have seen some linear algebra, let's take the 2 by 2 matrices, for example, with real coefficients under addition. Here, addition means that I'm going to add matrices E, F, G, H. We're going to add them component wise. So these would be A plus E, B plus F, C plus G, D plus H. And again, these are just 2 by 2 matrices where all the coefficients are real numbers. Then under this addition, this also satisfies G1 through G4. So it satisfies those same basic properties. So the addition of these matrices looks just like the addition of integers. Now, there are some other things that satisfy the same thing, but they start to look quite a bit different. So, for example, we have that R star. This is the reals except 0. So all the non-zero reals under multiplication. Then this satisfies G1. Is it associative? Yes, A times B times C. This is the same as A times B times C. And is there a neutral element with respect to this operation? So now our 0 is actually a 1. So there is an element, 1 is a non-zero real, such that when I apply 1 times A or A times 1, I get A back. So now my operation, instead of addition, is multiplication, and 1 is a neutral element with respect to that operation, so it works. G3, remember, it was inverses with respect to that operation. So for every non-zero real number, there is another real number, which is 1 over a, such that when I do the binary operation, which in this case is multiplication, and in any order I do it, I get back 1, which is the neutral element. So we do have inverses in this case. And I also have the commutativity. A times b is always b times a for any non-zero real numbers. So we also have that this satisfies all those four properties. And similarly, you can do the same thing with actually just non-zero rational numbers and their multiplication. They also satisfy the same property. However, if uh, if I take now instead of so how about if we try to do the same but with multiplication of 2 by 2 matrices with matrix multiplication. Now we run into problems because well, not everything is invertible. So we do have multiplication, and multiplication of matrices is associative. But for example, we're going to run into problems with the multiplicative inverses because if I have a 2 by 2 matrix and I want to invert it, then there is a rule that this is going to be something like AD minus BC times DA minus B minus C, I believe. And to have this matrix be an actual matrix in 2 by 2, we need this denominator to be non-zero. So this does not satisfy it doesn't satisfy G3. There are no multiplicative inverses as is, so it doesn't have those properties. However, if I restrict to what we call GL2 of R, which is 2 by 2 matrices with A, B, C, D real numbers, such that AD minus BC, that the determinant is non-zero, then this does satisfy that there are inverses, it's associative, there is a 1. What is the 1 in this case is what we call the identity matrix. The identity matrix has under multiplication, that is a neutral element under multiplication. However, it doesn't satisfy, so this will satisfy G1 through G3, but it does not satisfy G4. This is not commutative. Let me show you that we have matrices, for example, 1, 1, 0, 1, and 0, 1, 1, 0, such that, well, if I multiply them in this way, by the way, the determinant is 1 and minus 1, so these are non-zero determinant matrices. How do you multiply? This times this, and this times this, and so on. So I get 1, 1 times 0, 1, that is 1, 1, 1, 0. But if I go the other way and multiply this one times this one, then I get 0, 1, 1, 1. And these are not the same matrices. So there is so multiplication in GL2R is not commutative. So we see that, well, I mean, GL2R is something that is very important in linear algebra, in geometry. So we do want to know about the operation on GL2R. So that tells me that the last property we had, G4, should not be a complete requirement, that we can do a more general algebraic object that satisfies G1 through G3 without necessarily requiring G4. So when something satisfies G1 through G3, that we are going to call it a group. And when something satisfies G1 through G3 and also it is commutative, then we will say that that is an abelian group. Okay, and so let's see a couple more examples. Some of the examples of groups that are very important are those of symmetries. So let me show you the symmetries of a rectangle to start with. So I'm looking for, suppose I have a rectangle like this uh, with vertices A, B, C, and D, and I'm looking for operations that will leave this shape untouched. So I can transform it, but just so it ends up in the same shape. So for example, well, I can certainly just do the identity operation and do nothing to it, and that will leave me A, B, uh, C, D. I put a C here. Let me just so it matches my notes. C, D, and C, D. That will leave it exactly untouched. I can do a 180 rotation, so I can go from here to here by doing 180 rotation, and you see that a 90-degree angle would not respect the rectangle, but a 180 will bring A here, and then you can see that B will be here, and then C and D would be there. I can also do a vertical reflection, and that transformation will leave the shape also untouched, and now A would be here and B would be here, and I wrote C and D backwards again. C and D. So now C is there and D is here. So this is a vertical reflection. And I can also do a horizontal reflection. So if this was A, B, C, and D, then now horizontally this will be A, B, C, and D. So this is a horizontal reflection. Let me rewrite that. This is a horizontal reflection. And one way of finding more operations is that we can compose these operations. So these operations under composition, they are going to form a group that satisfy properties one can show. They satisfy properties G1 through G3. So the composition of these operations could produce new operations. So let's see what happens if I do. I'm going to do a composition. I'm going to start with my rectangle A, B, C, D, and I'm going to do first 180 degrees. And if I do 180 degrees, then I end up with A, B, C, and D. And then let's do our vertical reflection. So if I do a vertical reflection like this, then I'm going to end up with A, B, C, and D. And then we see that actually the composition from here all the way to here, what we accomplished is the same as a horizontal reflection. So I didn't really get anything new. But let's see what happens if I do it in the opposite order. So I'm going to first do the horizontal reflection. So no, I'm sorry, I'm going to do first the vertical reflection. If I do the vertical reflection, then I get A and C and B and D. And then I'm going to apply 180 degrees. So if I apply 180 degrees, I end up with A here and then B will be here, and C and D will be there. And you see that actually, when I do this composition, I get again the horizontal reflection. So the composition of these two operations is actually commutative, and that is this is in fact all the operations one can do in a rectangle, these four that I have described, and it is a commutative operation. However, this is not always the case with symmetries of objects. So, for example, let's see what happens with the symmetries of an equilateral triangle. So let's take a triangle ABC that is equilateral, and then there are several operations I can do. I can do, for example, vertical reflection, like so, and that is going to lead me to A is going to be put and get a B and C here. And I can do also rotations, in this case, a 120-degree rotation that will bring A here and C here and B here. Let's try again, do the combination of those operations, but in the opposite order. So I'm going to start with A, B, C, and then first do a 120-degree rotation so that I have A and B and C. And then I'm going to do a vertical reflection. So now my vertical reflection will keep C here, and A will be here, and B will be here. And now we see that actually I ended up with a different triangle by doing the operations in different orders. So what we get here is that this is a non-commutative group. So this is an example. So the operations on the symmetries of a triangle, of an equilateral triangle, under composition, it is a non-abelian or non-commutative group. One can show again that it satisfies all the other properties. The composition is associative. There is an identity operation, and there are inverse operations to all of these. However, it is not a commutative, as I've just shown. The operations do not commute. If I do them in one order or in the opposite order, I get different results. So I get different operations like that. Okay, great. So that is it for today. What we will do in the next video is actually do even more abstraction of the integers. What we're going to do is define the integers axiomatically, and then take those axioms and, for one thing, show that there are other objects that also have, as the integers, they have an addition and a multiplication. And then also we will prove a few things from the axioms of the integers. Okay, until then, bye-bye.